let's see how resonance structures can affect the hybridization of atoms and therefore affect the geometry. So let's check out the most famous example of this, and that is an amide linkage. So if you remember from our earlier videos on functional groups, right, that would be an amide linkage, a carbonyl next to a nitrogen like that. So what is the hybridization state of a nitrogen in an amide? Well, remember, we found the hybridization state by calculating the steric number, which is the number of sigma bonds plus the number of lone pairs of electrons. So around that nitrogen, there are 3 sigma bonds and 1 lone pair of electrons, giving us a steric number of 4, implying that nitrogen is sp3 hybridized. So the question is that nitrogen actually sp3 hybridized? If it is sp3 hybridized, this nitrogen will exhibit trigonal pyramidal geometry around it. So let's look at any possible resonance structures for our amide functional group. Well, for our patterns, I have a lone pair of electrons on my nitrogen next to a pi bond in my carbonyl. So I can draw a resonance structure, right? I can take this lone pair of electrons and I can move it in here to form a new pi bond between my carbon and my nitrogen. That would cause carbon to violate the octet rule, so we also must take the pi bond from my carbonyl and move those electrons out onto my oxygen. So let's see what we would get for our resonance structure if we move our electrons like that. So I have my R group here. My oxygen used to have 2 lone pairs of electrons around it. It just gained another lone pair from that old pi bond, so now it would look like that. Carbon used to have 1 bond between carbon and nitrogen, but the lone pair of electrons from nitrogen has moved in to form a new pi bond, so we would get this as our resonance structure. Right? So we need to assign formal charges. So this oxygen has a -1 formal charge, nitrogen has a +1 formal charge down here. Watch the video on formal charges if you do not know how to assign them yet. What is the hybridization state of nitrogen in this resonance structure? Well, now it has only 3 sigma bonds around it, right? Because one of these is a pi bond in here. So there's only 3 sigma bonds, 0 lone pairs of electrons, giving me a steric number of 3, implying this nitrogen is actually sp2 hybridized. So which one is it? Which is nitrogen sp2 hybridized or sp3 hybridized? Because remember, resonance structures do not resonate back and forth. This nitrogen is not switching from sp3 hybridization to sp2 hybridization. It is not going from a trigonal pyramidal geometry over here on the left to a trigonal planar geometry for my sp2 hybridized situation on the right. Turns out whenever a lone pair of electrons participates in resonance, in order for that lone pair of electrons to participate in resonance, that lone pair of electrons must occupy a p orbital. That tells me that this nitrogen is actually sp2 hybridized, since an sp2 hybridized nitrogen actually has a p orbital, and sp3 hybridized does not. So this nitrogen is actually sp2 hybridized with that lone pair of electrons in a free p orbital and giving me a planar geometry of atoms around my nitrogen. So let's look at our amide functional group again, and let's take a closer look at the hybridization of some of the other atoms in my amide functional group, right? So I have this as my dot structure, and we've just proven that even though this nitrogen looks like it's sp3 hybridized in this dot structure, because that lone pair of electrons participates in resonance, that lone pair of electrons occupies a p orbital, meaning this nitrogen is actually sp2 hybridized. What about this carbon right here? Well, number of sigma bonds around it. It actually has 3 sigma bonds, right? Because one of these in this carbonyl is actually a pi bond, and 0 lone pairs of electrons, giving me a steric number of 3, telling me that this carbon is actually sp2 hybridized, and it will have trigonal planar geometry of all the atoms around it. So since oxygen is attached to that carbon, this oxygen will be in that planar arrangement of atoms, and this oxygen has 1 sigma bond around it, right? One from this carbonyl, and 2 lone pairs of electrons, so it is also sp2 hybridized, indicating this oxygen will have a p orbital. So I have nitrogen, carbon, and oxygen are all sp2 hybridized, which means they will all have p orbitals. And the arrangement of these atoms must be planar, right? Because carbon is planar, nitrogen is planar, so these atoms are forced into a planar geometry, right? So if I wanted to represent all of those atoms on a flat sheet of paper, since those atoms all exhibit planar geometry, right, I could fit all of those atoms on a flat sheet of paper. So let's attempt to draw those atoms, and let's indicate the planar geometry of those atoms, right? So they're all flat. They're all on that sheet of paper. And oxygen has a p orbital since it's sp2 hybridized. So I'll go ahead and draw my p orbital here. Carbon, same thing. It has a p orbital, and same with nitrogen. So the electrons in my resonance structure are actually delocalized or spread out in these p orbitals, right? And the delocalization of those electrons from my resonance structure gives extra stability to this molecule. So an amide bond is actually very strong. And that's a good thing. In biochemistry, an amide linkage between two amino acids is called a peptide bond, and this is what holds proteins together. So this turns out to be an extremely important functional group with an extremely important relationship between the carbon and the nitrogen. Right? It's actually a very strong linkage, and the atoms are planar. So extremely important concept in biochemistry all comes down to understanding how resonance structures affect the hybridization of atoms. Let's do another example where the resonance structures will affect the hybridization of an atom, and let's do the resonance structures for pyrrole here. So here is pyrrole, lone pair of electrons on my nitrogen, and once again I first start by looking at this nitrogen saying, what do I expect the hybridization state to be? 3 sigma bonds, 1 lone pair of electrons, so I would expect the hybridization of that nitrogen to be sp3 hybridized. Let's see if I can draw any resonance structures, right? Well, the pattern of a lone pair of electrons next to a pi bond tells me that I can. So I'm going to take this lone pair of electrons and move it in here. That would give too many bonds to this carbon. So this old pi bond is going to have to move, right? So it's going to move, and it's going to kick those 2 electrons from that pi bond off onto this carbon down here. So let's see the resonance structure that would result from the movement of those electrons, right? So let me just draw my carbon skeleton here. And this lone pair of electrons moves in here to form a new pi bond, right, between the nitrogen and that carbon there. This lone pair of electrons moved out onto this carbon, and then this old pi bond stays right there. So let's check out any formal charges that results, right? If I do formal charges on this top nitrogen here, I'm going to get a +1. What about this carbon down here? Well, this carbon down here actually has a hydrogen attached to it, right? So over here there's actually a hydrogen attached to it. So that would actually give me 3 bonds to this carbon, and 1 lone pair of electrons give me a negatively charged carbon, so a carbanion. So this carbon is actually negatively charged. So let's check out the hybridization state of nitrogen, right? So this nitrogen now has 3 sigma bonds around it and 0 lone pairs of electrons, giving me a steric number of 3, implying sp2 hybridization. And since this lone pair of electrons participates in resonance, right, this nitrogen is actually sp2 hybridized, so very similar to the situation before. So that lone pair of electrons occupies a p orbital, and nitrogen is actually sp2 hybridized. What other resonance structures could I draw, right? There are a couple more I could draw. I could say, right, I have a negative charge next to a pi bond, so I could move these electrons in here, and these electrons could kick off onto this carbon for my next resonance structure, right? So let me just draw my next resonance structure, right? There's my old pi bond. I just made a new pi bond, and I have a lone pair of electrons on that carbon right there. This nitrogen had a hydrogen here, so my formal charges, right? My formal charges, this nitrogen would be positive, and this carbanion would be negatively charged like that. So I could keep going. Right? I could keep going with my resonance structures. I could say this lone pair of electrons could move in here. That would be too many bonds to this nitrogen, which means that these electrons would have to kick off onto this carbon right here. So what would I get from that resonance structure? So let me draw my nitrogen with my hydrogen, and let me put in my carbon skeleton here. Right? This was my old pi bond. It didn't move. Right? But over here, those electrons moved in here to my nitrogen like that, and then these electrons over here kicked off onto this carbon right here. So now I have this situation. New formal charges. New formal charges. Now my negative charge is over here, and this nitrogen is actually positively charged. So I would have this situation. I can draw one more resonance structure, right? I can show the movement of these 2 electrons into here to form a new pi bond, and that would mean that this old pi bond would have to kick off onto this carbon this time. So let's see what that would give us, right? So now I have a resonance structure with, let's see, this is my old pi bonds over here on the right, so I'm going to make a new pi bonds right here. And then now my negative charge is right here on this carbon. So my lone pair of electrons is on that carbon, giving me a negative formal charge right here, and this nitrogen is still positively charged, right? So if I wanted to, I could get back to my original dot structure, right? I could get back to this by showing the movement of electrons from this last resonance structure here, right? If these electrons moved in here, and then these electrons moved off onto my nitrogen, I would get back my original dot structure here for this molecule. So we've actually done some resonance structure practice here, but the point of these resonance structures is to show you that most of the time nitrogen has a pi bond connected to it, and since those electrons are in that p orbital, this nitrogen is actually sp2 hybridized. Let's look at one more quick example, which is very similar to this example, except we're going to replace the nitrogen with an oxygen. So let's see what would happen if we replace the nitrogen with an oxygen. Well, we need to have an octet on my oxygen, so I can go ahead and put in 2 lone pairs of electrons like that. And if I think about the hybridization state of this oxygen, 2 sigma bonds plus 2 lone pairs of electrons give me a steric number of 4, implying that this oxygen should be sp3 hybridized. So is it actually sp3 hybridized? Well, this lone pair of electrons right here can actually go move in here, right? And then this lone pair would have to kick off, this pi bond, I should say, should have to kick off onto that carbon. So we actually do have a resonance structure for this molecule, right? So let me go ahead and draw my carbon skeleton in here. So there's actually a pi bond that forms right there. My old pi bond is over here, and I get a lone pair of electrons on this carbon, right? There's still a lone pair of electrons on that oxygen, so this would be my resulting structure. My formal charges, I get a carb anion down here, right? A negatively charged carbon right here. This oxygen now will get a positive charge, right? So those are my formal charges. Now, what would the hybridization state of this oxygen be? 2 sigma bonds, right, because one of these is a pi bond. So 2 sigma bonds plus 1 lone pair of electrons give me a steric number 3, saying this hydrogen is actually sp2 hybridized. And since this lone pair of electrons over here, the ones I circled in blue, actually participate in resonance, they must occupy a p orbital. And if they occupy a p orbital, that implies that this oxygen is actually sp2 hybridized. So it is actually sp2 hybridized, which means that one of its lone pair of electrons in the original dot structure will participate in resonance and occupy a p orbital, and this other lone pair of electrons here, right, these right here that are still on the oxygen, this lone pair must be in an sp2 hybridized orbital. So that's a new situation there, and we don't have time to draw all of the other resonance structures, but it's just like the one above, so you can go ahead and do that for practice. This concept of resonance structures affecting hybridization states will be very important when we talk about aromatic molecules.